Calculus is like a big toolbox, giving us different tools that can help us find out the relationships around us. Calculus offers layers of tools to tackle the problems around relationships. The outer layer provides the ultimate tools to handle these problems. Taylor series expansion helps us understand relationships. Fourier analysis helps us analyze relationships. And optimization helps us construct relationships. Differential equations help us find relationships. In order to do this, calculus needs to develop the intermediate tools, basically differentiation and integration. They power these ultimate tools you can use. So in this course, we will talk about different differentiation and integration techniques. But they are confusing and difficult. Personally speaking, if I don't see the purpose of doing something, I will struggle with following the steps. So in order to be engaged in learning the mechanics, you need to understand why they are important. So in the next video, I want to let you know what differentiation and integration are and why they are important. Differentiation and integration, they power these ultimate tools you can use to tackle relationships. But what are differentiation and integration, and why would they help us with these ultimate tools then? Then you need to understand calculus' main object, relationship. Relationship has to be between at least two things. If there is a relationship between two things, then it means one will change with the other. So relationship between the two and the relationship between the two changes, they are two sides of a same coin. Differentiation and integration are the two forces that can get us from one side to the other. If you know the relationship, you can use differentiation to find out how they change. On the other hand, knowing how one changes with the other, you can use integration to find out their relationship. But how can knowing this be useful to the ultimate tools then? First, differentiation and integration help us understand the fundamental relationships. For example, up to the calculus age, our understanding of sine is just a table, listing the correspondence between the angle and the sine value. Given an angle, you can look up the sine value. But we didn't really understand their connections. We didn't really know how to turn the angle into the final sine values. But in the post-calculus era, the knowledge of sine is a full-blown relationship, a relationship between the angle and the sine value. Through differentiation, we find out how sine changes with the angle. Then integration brought all those impacts from the changes together, giving us a Taylor series expansion for sine. In other words, we understand sine in terms of how sine changes with the angle. Understanding the relationship in terms of how things change is the basis for Taylor series expansion. This method offers a way to understand some of the most fundamental relationships, like sine, arcsine, and log. Those well-understood relationships will be used to analyze, construct, and find relationships. For example, the sine relationship is used in Fourier analysis. It's widely used in sound analysis. If you're interested, you can find more details in our course, How Calculus Helps Us Understand Trigonometry. In data science, you need to model or construct the relationships. You observe data. You try to come up with the math models that can imitate the relationships. What you would do is to pick different basic functions, combine them properly to mimic the relationships observed. But there are many different choices. Calculus provides the optimization tool that can help us find a best model quickly. How does it do that? Differentiation is a critical tool in optimization technique. It helps us understand how our model performance changes with different model choices. It guides us to find the best model quickly. Now, how about finding relationships? In natural science, we want to find relationships. what we observe is an equilibrium. That equilibrium is transformed into a math equation involving the unknown relationships and the changes. So how to solve these kind of equations then? Now what you need is not just the one-sided tool of either differentiation or integration. You need both. What you need is to get familiar with a pair of functions and their derivatives. Only then is it possible to guess what kind of pair will form an equation like this. Okay, so we have a better understanding about the purpose of doing differentiation and integration. The next question is how to differentiate or integrate exactly. We're talking about the exact mathematical mechanics. We will see that next. After we have a better understanding about the goal of doing differentiation and integration and why they're important, now we're to talk about the mechanics, the mathematical steps. So how to do differentiation and integration then? We have actually started doing this at a young age, far before studying calculus. Knowing the change, we know how to formulate the relationship. If we know a car's speed, we multiply it by time t. This is the relationship between distance and time, telling you the distance for any time. This is forming a relationship between distance and time. Of course, the relationship can be between any two things, x and y. Knowing how fast y changes with x, we can formulate y in terms of x. Just multiply velocity by x. On the other hand, if we know the relationship, we can find out the speed. In this case, it's so simple that we could identify it immediately. So in this simplest case, no integration or differentiation is ever needed to get from one side to the other. So how things get complicated then? That's because the change is not constant. It means y will respond to different x differently. For example, when x is small, changing x will induce a small change in y. But when x is large, same amount of changing x will induce a larger change in y. So the velocity is also changing with x. However, if it changes in an orderly manner, then we can still get the relationship through integration. Say the velocity is linear. But now you can't multiply velocity by the overall x because it's changing all the time. You need to chop the overall x into smaller steps. Use the velocity formula to get a velocity for each interval. Then you use the incremental velocity times the interval to get each increment. Then add them together. This is what? All these are incremental changes of y in terms of x. So they add up to the final y. However, you won't get a general relationship unless you use abstract symbols. Let's say the velocity is 2x. So that means y changes with x at the speed of 2x, meaning that the velocity gets faster. So the general relationship won't be this easy. What I mean by using abstract symbols is you don't use specific numbers for x or the number of cuts. You keep them abstract. Say if you pick a specific number x and m, then you are adding a bunch of numbers. Sure, you will get a value for y, but the general structure is lost. Also, the answer is not accurate because you're assuming a constant velocity during each interval. But if we keep them both abstract, using algebra to carry out the aggregation, we are able to patch back these little increments into the final status x. Hence, we get a general relationship between the two, with a narrow term here. Why would a narrow term show up here? That's because we're using an imperfect tool. We are assuming constant velocity during each interval. But it gives you a glimpse of the accurate answer if you set the arrow to 0. That happens when we make more and more cuts, so the error will be smaller and smaller. But there is a logical conflict here. The increment cannot really be 0, because if it is, then this whole thing would be 0 from the beginning. So the concept of taking the limit was born. We evaluate this aggregation when the increment approaches 0. That's the limit of this inaccurate tool. This way, we get a general and accurate relationship. So starting with this relationship of change, through integration, we can find out the master relationship. On the other hand, if we start with this relationship, through differentiation, can we back out this velocity then? Again, the calculation has to be done symbolically if you want a general relationship. You can't choose a specific observation point because velocities are different, so you need to keep it abstract, call it x. This subtract and divide approach is not accurate either, because the velocity is changing all the time. The speed calculated this way is only the average speed during the interval. Hence, this window represents the error because of this imperfect method. So you don't want to fix it, you leave it flexible. Then using the relationship, we can break down the subtraction into components. Factor the denominator. Now we can take limit to obtain a general and accurate relationship for velocity. So, symbolic calculation is at the heart of calculus. Only through the use of abstract symbols can we obtain an accurate and general relationship. These are the very basic differentiation and integration techniques. They are used when relationship is simple. But when the relationship gets complex, are these basic methods enough? Are there any other methods? To answer this, we need to talk about how should calculus prepare us to tackle real-world relationships, which are more complex. So we have a brief understanding about the ultimate purpose of doing differentiation and integration. Also, we know the basic techniques of differentiation and integration. The next question is, how does calculus prepare us to tackle the real-world relationships? Then you need to understand how the real-world relationships look like. Real-world relationships are way more complex, but a lot of them can be understood in terms of a few fundamental ones. So what are these fundamental relationships? The 3 fundamental relationships were inspired by natural phenomena: acceleration, cyclical, and natural change. For each relationship, depends on what is known, what is unknown. Each branches into 2. This leads to the 6 fundamental functions for math operations. We can combine and mix these fundamental ones to understand the more complex real-life relationships. There would be an infinite number of ways to form a complex relationships using the basic ones. But that doesn't mean calculus needs to differentiate or integrate each possibility. Calculus only needs to focus on these fundamental ones. And then, to tackle more complex relationships, it needs to come up with the combination rules for differentiation and integration. So in the next few sections, we will talk about the techniques that can help us differentiate or integrate the fundamental functions, and then the combination rules for handling more complex ones. In this section, we will see how to differentiate the fundamental functions. These 3 functions are relatively easier to understand. That's why they are called functions, while their counterparts are called inverse functions. For these easier functions, direct differentiation is possible to get their derivatives. But for these inverse ones, differentiation tricks will be used. We will first see how to differentiate this polynomial. To differentiate this polynomial, we let input slide a bit, and the output. Divide the two, and then take limit. We need to break down this complex term in two components. The method used is called binomial theorem. We'll do a brief overview here. Let's start with this simple case, where we multiply twice. Now let's break it down into two multiplications. Let's graph them here to see more clearly. Starting from 1, the multiplication branches into 2, times A and times B. Then going to the next level, each will multiply by A and B. Aggregate the terms. This is what we get. Now, if we add another layer of multiplication, now each node branches into 2 again, times A times B. Then aggregate the terms. This is what we get. Now let's think about why we have such terms. That can be understood if we know their meanings. For example, A cubed means it multiplies by A 3 times, by B 0 times. A squared B means it multiplies by A twice, times B once. AB squared means times A once, times B twice. And B cubed means times A 0 time, times B 3 times. Then let's think about the number of each term. For example, why we have 3A squared B? That's because there are 3 ways to multiply by B once. Multiply it in the beginning, in the middle, or in the end. So that means we can think of these 3 as the number of ways to pick one period out of 3 for multiplying by B. So it is a combination problem. Let's use this notation. It means the number of ways to pick 1 out of 3. The first coefficient means the number of ways to choose 0 out of 3. And this is the number of choosing 2 out of 3. And the last one is the number of 3 out of 3. Now we can deal with more general case, where there are n multiplications. First, we think about the types of terms. We have a to the power of n times b to the power of 0, meaning multiply by a n times b 0 times. And the number of it can be obtained through thinking about the number of ways to choose 0 out of n. Then we have a to the power of n minus 1 times b. The coefficient is the number of ways to pick 1 out of n. And so on, until a times b to the power of n minus 1. The coefficient is picking n minus 1 out of n. Then the last one, a 0 times b n times, with a coefficient of picking n out of n. Add them together, we have the expansion. Now, for our case, plug in the expansion here. Here we need to figure out those coefficients. The first term is easy to see there is only one way to choose 0 out of n. So this is 1. What about this term? Choosing 1 out of n for multiplying by delta x. We could pick the first one, the second one, third one, and so on until the last one. So how many in total? N, right? So this is n. What about the rest of them? Here is the formula for these binomial coefficients. You can check out my video Binomial Theorem for more details. But actually here for this case, you only need the first 2 terms. Here's why. These 2 cancel out. Then we can factor out the delta x term. Once you've done that, now the limit process will make any terms involving delta x vanish. So we're left with n times x to the power of n minus 1. We got our first derivative. Next, we will differentiate the exponential function. In this video, we will differentiate the exponential function. Before we differentiate, I should remind you that in real life, the exponential relationships we observe are rarely base e. They can be any positive numbers, but they will always be converted to base e, because only base e can be computed. If you want to know more details, you can check out our video on math language and expressions. Hence, the real-life exponential relationship will have a certain constant on top. It represents different speed of growth. Now let's differentiate this general exponential function. The key is this computing formula for exponential function. Take the difference, divide over delta x. Now take out e of ax. The formula for e can be used to expand this delta term. These two cancel out. Now we can factor delta x, giving us a plus the higher order terms. As we take the limit, only constant a stays. All others will go away. So we are left with a times e of ax. So the derivative is a times itself. Next, we will differentiate sine x. Now we will differentiate sine x. Using the definition, it's the sine difference divided over delta x. Now to break this down, we need a combined angle formula. Aggregate them, breaking it into two parts, and we will tackle each part individually. When we take the limit, only the terms involving delta x will matter. So we can take sine x and cosine x out of the limit. And this limit is 1. This is 0. I'll explain why. For the first part, we will use geometry to analyze it. If we use a unit circle, it can help us visualize these numbers. Say this is angle delta x. This height will be sine delta x. But we're not comparing sine change to the angle change, because they're incomparable. One is the angle and the other is length. Instead, we're comparing sine change to the arc length facing the angle. Because although one is straight line, the other is a curve, at least they are both lengths. They're more comparable. So personally, I think the only reason we're using arc length instead of the angle is due to calculus, because we want to make them more comparable. Now, let's see if it makes sense to think that the limit of these two ratios would approach 1. When the angle is big, it's hard to say how these two compare. But as the angle gets smaller and smaller, seems that the height is similar to the arc length, right? So it's worthwhile to try to prove this. To compare the two, we consider three areas. First one, the triangle OAB. Then, the slice OAB. Finally, the triangle OAC. Triangle OAB should be smaller than the slice OAB, smaller than the triangle upside. The first triangle has an area of 1/2 sine delta x. The area of the slice is half the arc length. Here's why. The slice area is a fraction of the overall area, which is the angle divided over 360 times pi. Pi is the area of a unit circle. But also remember how we define arc length. It's a fraction of the overall circumference. The fraction is also the angle divided over 360, but the circumference is 2 pi. So this is arc length. Hence, the slice area is half the arc length. Finally, the area of triangle OAC equals to 1/2 times the length OA times the height CA. OA is 1. CA over OA is tangent delta x. OA is 1. Tangent is the ratio of sine over cosine. Hence, CA is this ratio. 1/2 can be crossed out. All we need is to divide over sine to make the ratio appear. So we end up with a relationship saying 1 is less than the target ratio, less than 1 over the cosine. Let's place them on the number axis. 1 is here. 1 over cosine is here, greater than 1, because cosine is smaller than 1. This target ratio is somewhere in the middle. What will happen when the angle approaches 0? Inverse cosine will get closer and closer to 1. So this ratio has to go along as well, because it's sandwiched in the middle. Hence, the limiting value of this ratio is 1 as the angle approaches 0. This is the sandwich theorem you can use to prove limits. So in our case, the target ratio is not well understood, but we place it between something we have better understanding of. So we proved the first part. Now we need to show the second has a limit of 0. We don't need geometry for this proof. Algebra will do the work. The double angle formula will be used for here. Rewrite the cosine delta x as twice the half angle and plug in this formula. Cross out these and take the minus sign to the front. Then place 2 in the denominator. Now let's split this sine square into 2. Now, the familiar ratio shows up, and we already know what it is. We take the limit, and the limit can be split into 2. The first limit is 1, we already proved it. The second is 0 as the angle or the radian approaches 0. Hence, this limit is indeed 0. So the derivative of sine is cosine. Next, we will differentiate their inverse functions. We will not use the differentiation definition because the inverse functions are not well understood yet. By using this formula, we find out the derivatives for these 3 functions. Then, how to differentiate these inverse functions then. What's different now is, going through this definition approach won't work this time. The reason is, we don't know much about these operations in the first place. Unlike in the case of original functions, we have some understanding about the operations. That's why we're able to break down a complex term into smaller components. But this time, for the inverse, we don't actually know much about them. We're unable to break them down into simpler terms. But we will use a trick called inverse derivative rule to get the derivatives. In my future course, you will see we will actually use their derivatives to construct the inverse functions. Now let's talk about this inverse rule. So there is a relationship between x and y. Functions and inverse functions are 2 directions to compute the unknown based on the known. When x is known, y is the unknown. Let's say function f is used to compute y based on x. On the other hand, when y is known, x is unknown, function g is used to compute the unknown. This is the inverse function as opposed to the original one. The inverse derivative rule says there is a connection between the two derivatives. The product is 1. Before we see how the math works, let's think intuitively why it makes sense. Let's use running as an example. If the girl runs 3 times as fast as the boy, then the girl's speed in terms of the boy is 3. But we can also switch around using the girl's perspective. So the boy's speed in terms of the girl is 1/3. Now let's think about what these ratios are. The first ratio is the girl's speed in terms of the boy. That's G prime. The second ratio is the boy's speed in terms of the girl, B prime. The product of these two ratios is 1. Now let's see how the math works. This is how we get the derivative for f. But don't forget its meaning. It's the limiting ratio of the two changes telling us how fast y changes with x. Similarly, the derivative of the inverse tells us how fast x changes with y. It's the limiting ratio of the inverse. It can be written as the inverse of delta y over delta x. Now you can pass the limit operation to the numerator and the denominator respectively. Constant remains the same. Now what is this guy? Remember, there is a connection between the two. So that implies if x changes a little, y changes a little, and vice versa. This is an important property of continuous function, as we will explain more in detail later. What this property allows us to do is, we can change from delta y to delta x. Because y changes a little means x changes a little. Now we can recognize this is how fast y changes with x, or the derivative of f. Hence, the product of these two derivatives is 1. This rule allows us to get the inverse derivative easily. Now we have the inverse derivative rule in our arsenal. We will use this rule to tackle the nth root first. In this video, we will apply the inverse derivative rule in getting the derivative for the nth root function. Let's call this function f. To get its derivative, think of the inverse. If y is the nth root of x, that means x is y to the power of n. Call it function g of y. We know its derivative is still a polynomial, power reduced by 1. Now using the inverse rule, f prime would be the inverse of g prime. But the only problem is, y is the unknown. We need to replace it with the known x. Y is the nth root of x. Plug it in here. The power term can be simplified as 1 minus 1 over n. Inverted, we get f prime as 1 over n times x to the power of 1 over n minus 1. So we're able to fill in one more blank. Actually, if you compare these two, whether the power term is an integer or a fraction, the differentiation rule looks pretty consistent. Power term becomes the constant in front, then power term reduced by 1. Next, we will tackle log, the inverse of exponential function. In this lecture, we will use inverse rule to differentiate log function. Let's call it fx. To get its derivative, think of the inverse. Log gives us the growth rate. So, y is the growth rate. If we use it on top of e, it gives us the growth result, x. Call it function g of y. Its derivative is itself. Using the inverse rule, f prime is the inverse of g prime, which is 1 over e to the power of y. Now we just replace the unknown y in terms of x. e to the power of y is x. So plug it in here. Derivative of log x is 1 over x. Next, we will tackle arcsine, the inverse of sine. Now let's tackle arcsine. Let's call it function f of x. To get its derivative, think of the inverse. Arcsine gets you the angle. Hence, y is the angle here. X is the sine value. Therefore, x equals to sine y. Call it function g. We know its derivative is cosine. Now, using the inverse rule, f prime would be the inverse of g prime, which is 1 over cosine y. Now we need to replace y with x. According to this relationship, cosine y is the square root of 1 minus sine squared, plus or minus. So plug it in here. And this is x squared. But there are two possibilities, plus or minus. So what does the sign mean here? Y is the angle, x is the sine value. So the derivative is the limiting ratio of the two changes, telling us how fast the angle changes with sine. Let's put a graph here to see clearly. If we consider the angle from 0 to 90 degrees, as the angle increases, so does the sine value, until it reaches max 1. So the ratio of these two would be positive within this range. Then as angle continues to increase, sine value starts decreasing until it reaches negative 1. This ratio would be negative. Then as angle increases, sine value goes up again, and this range is positive. Hence, there are two possibilities for the derivatives of arcsine. The positive one for the angle between negative pi over 2 to positive pi over 2. And the negative one is for the angle between pi over 2 to 3 pi over 2. We have the derivative of arcsine. So we have finished differentiating the 6 fundamental functions. Next, we will talk about how to integrate them. In the last section, we learned how to differentiate these fundamental functions. The next question is how to integrate them. In the introduction section, we briefly talk about the aggregation method of integration. In this video, we will talk about integration in more details, and you will see the challenges with direct integration. When you're doing integration, you're given a function, and you're asked to integrate it. You have to understand what information you are given and what result is expected. The function to be integrated means the relationship between the two changes. Integrating it means you want to find out the primitive relationship between the two by using the information about how they change. Let's go back to the example where we integrate this linear function. The way we patched up the overall relationships, we assume that both x and y start from 0. That's why x starts with the first increment, and all these increments add up to y. But what if x starts from a certain status, say A, and y starts from h? Now we need to update the starting point and offset these by a. We also need to adjust our integration notation to remind us that we are adding these incremental changes when x changes from a to x. But then we have 2x showing up. This x is the flexible upper bound we're accumulating to. But this x is the running notation, meaning all the intermediate points from a to x. To avoid confusions, we will change this running notation to another symbol, say t. But the meaning remains the same. Aggregate the incremental changes at the speed of ft, when t changes from a to x. But remember, these incremental changes add up to the change in y, instead of the final status of y. So this is delta y. You can carry out the algebra as usual. Adding a constant a here makes the algebra a little bit messier, but not too much. But note that when you piece together these increments of x, it's the net change of x minus a rather than x. Carry out the limit process, we have x squared minus a squared. This is the net change of y. So to get y, you just add the initial status. This is still a relationship with respect to x plus some constant. The part involving x is the part causing the change. The constant relates to the initial conditions. Now if we start with a different set of initial conditions, say b for x and k for y, the only difference is in the constant. The core relationship stays the same. So, given the function of how two things change, integrating from the initial start up to x will give us the net change of y. In this case, it will be a quadratic term. At the initial y, it will give us y, but not just one value for y, but a relationship telling us how to compute y for any x. It has a core relationship involving the change plus some constant. What this constant is depends on the initial conditions. When the integration symbol has a lower bound, upper bound of x, this is called indefinite integral. Theoretically, you can carry it out using algebra, but it could get very difficult. Let's say we're integrating an exponential function. So we're given one thing changes with the other exponentially. In order to find the core relationship, we need to assume x starts from a certain condition up to x. Then to carry out the integration, we will chop the overall change of x into n intervals. Use the velocity formula to find out velocity for each interval, multiply by the interval, aggregate them, and take the limit. But here's the tricky part: how to aggregate these many exponential terms. We hope they will collapse into a compact formula involving only x plus some constant due to the initial conditions. But the algebra isn't that easy. So when the velocity term gets complicated, you could have a hard time carrying out the algebra. This is the challenge with direct integration. In the next section, we'll talk about fundamental theorem of calculus and see how the theorem can help us in this case. Now let's take a look at the theorem to see exactly what it is saying. It has been confusing to a lot of people. It has two parts. The first part is reinforcing that integration and differentiation lie on the full circle. It starts with the relationship of the change. You use integration to patch back their primitive relationship. But because of the initial conditions, there would also be a constant. Then if you differentiate this patched relationship, you should get back the relationship of the change. An alternative version of this theorem starts from this end, the primitive relationship. Now we know the relationship between the two, we can use differentiation to find out the derivative. That's the relationship between the two changes. Then if we integrate this derivative, we will get back the relationship plus some constants. Now, notice that we have this full circle. Although it means differentiation and integration can get us back and forth between the two ends, they are with different difficulty. Integration is difficult. Differentiation is easier. For example, when asked what's the integral of cosine, this aggregation method could be difficult. But we know cosine is the derivative of sine. Hence, when you integrate it, you should get back sine plus some constants. because if we put sine on the circle, differentiate it, you get the derivative of sine. Then integrate it, you should get the sine back. So here's an alternative version of this theorem. When asked to integrate certain functions, if you can recognize whose derivative this function is, then that's the answer, plus some constants. You don't need to carry out the tedious integration process. Now, because no actual integrations will take place, we can get rid of the bounds. It means use the trick to find out integration results. Part 2 of the theorem is telling us a handy way to evaluate an integral. First of all, what does this integration symbol mean? This is called definite integral, where you have clear bounds integrate from a to b. What it means is, when x changes from a to b, how much y changes. This theorem is saying there is an easy way to find out, and this is the hard way. Aggregating derivative term little by little from a to b. The easy way is saying, hold off doing the arithmetic. You know how y changes with x. You can use that to find out the relationship between x and y. This relationship can tell us what y is given x. When x is a, y is fa. When x is b, y is fb. So how much y changes? Subtract the 2. So part 2 of the theorem is saying that whether you aggregate little by little or subtract the two end values, you will get the same answer. But I should warn you, this only works if you do have an explicit formula for the relationship. If you're integrating a normal density function, in theory, you can use the end formula to compute. But we haven't found out the explicit formula yet, so you can only use this numerical integration method. Okay, so now you understand fundamental theorem of calculus. In the next session, we will use it to finish our integration table. In this section, we will talk about how to integrate these fundamental functions. As we've mentioned last time, the fundamental theorem of calculus implies that if we want to integrate someone's derivative, we will get back that someone plus a constant. So, when integrating an integrand, if we can recognize it as someone's derivative, then the answer is that someone plus some constant. That someone, big fx, is called the antiderivative of small fx. Hence, for integration of these fundamental functions, we will try to find out their antiderivatives. That is, which function, when differentiated, will give us such integrand. Then that's the answer, plus some constant. The easiest way is the exponential function. The differentiation table is useful now. So if we differentiate e of ax and get a derivative of a times e of ax, then when we integrate it, we should get back e of ax. But here, we're not integrating a times e of ax. We're integrating e of ax. Let's adjust it a bit. We should get 1 over a times e of ax. For this polynomial, according to this rule, differentiate x to the power of n, we get n times x to the power of n minus 1. That means if we differentiate x to the power of n plus 1, we should get n plus 1 times x to the power of n, which also means if we differentiate this guy divided over n plus 1, we will get x to the power of n. Therefore, now if we integrate x to the power of n, we will get this guy. Similarly, the integral for the nth root of this guy. You can use this as a practice. What you need to do is, if you differentiate this guy, would you get back the nth root? What's remarkable about this approach is, We don't need to go through the painful algebra to arrive at such conclusion. So if you want to find out the integral of sine, what you need to do is to find out which function, when differentiated, will give you sine. If you do that, you will find differentiating negative cosine x will give you sine x. So that means the integral of sine x is negative cosine x. I will talk about how to differentiate cosine at the end of this lecture. Right now, I want to point out the key message of this lecture. The job of doing integration actually becomes a job of doing differentiation. So if you are asked, what's the integration of this function? All you need to find out is which function, when differentiated, will give you this. And that's arcsine. Now we're done with these fundamental functions, except these two. They will be tackled after we learn the combination rules for differentiation and integration. We will see that in the next session. Now we will differentiate cosine x. Using the definition, it's the cosine difference divided over delta x. The combination formula for cosine is useful now. We use it to write the new cosine in terms of cosines of x and cosines of the change delta x. Subtract the original cosine, then divide it over delta x. Combine the two terms with cosine x together. This is what we get. As usual, we will split it into two. Sine x and cosine x has nothing to do with the change, so we can move them out of the limit. Now we end up with two limits. Looks familiar, right? In the previous video, in order to get the derivative of sine, we already confirmed these two limits. So here, the first limit is 0 and the second is 1. We are left with negative sine x. So now we have the differentiation table for the 6 fundamental functions and the integration table partially filled. The next question is, how do we account for real-life relationships? They are complex, but a lot of them can be understood as made up from these basic ones. In this lecture, we will talk about the possible ways to assemble these basic ones in order to make more complex functions. And then, how to differentiate or integrate these complex relationships. Again, we will start with differentiation because it's easier. In this case, you don't want to use the definition approach because it's difficult. So first, let's think about what are the different ways to combine functions. Not surprisingly, we have the 4 basic operations: add, subtract, multiply, and divide. First rule, we can add 2 functions to get a new one. Then its derivative is the sum of the 2 derivatives. Then subtraction rule. If we subtract 2 functions to form a new one, then its derivative is the difference between the 2. These 2 are pretty straightforward. Then product rule. This is less obvious. If we multiply 2 functions to form a new one, then its derivative is the sum of each derivative weighted by the other function. I will explain this in detail now. The method starts as usual. Let the function slide a bit. Subtract the 2, divide over input change, then we take the limit. Let's work on this part first. For the first term, we make up an extra term, gx, then subtract it. Also for function h, we add hx, then subtract it. Carry the product. This guy is delta g. This guy is delta h. This way, the first term is gx plus delta g times hx plus delta h. Then we multiply term by term for the first product. We get this. Now subtract the product of g and h. These 2 crossed out, leaving us with these 3 terms. Then divide over delta x and take limit. As we have shown before, the limit of the sum of three terms can be broken down into the sum of three separate limits. hx has nothing to do with delta x. Take it out of the limit. This limiting ratio is just g prime. Similarly, gx has nothing to do with delta x. Take it out of the limit. This limiting ratio is the derivative of h. The third one can be broken into two products. The first part is just the derivative of g. The second part is what? hx is the mechanism converting x to h, let's say. If hx is continuous, then if x changes a bit, so does h. Hence, this part is 0. So we're left with these two products. Now for a quotient, what is the derivative? We can convert this division problem into a multiplication one. If we assume fx is differentiable, then we can apply the product rule. We know fx equal to these two, so we substitute fx with this ratio. Now, f prime is what we want to get, so we move this term to the left, then divide over hx. We can combine these two if we multiply g prime by hx over hx. It's the mixture divided over hx. With the hx below, now we have this mix divided over hx squared. Aside from these four basic ways of combination, one of the most important ways is through compose. You combine two options in a layered way. You perform a first operation, h, on the input x, then use the intermediate result as input to the second layer operation, g. In the next lecture, we will understand how to get this derivative through chain rule. To understand how to get this derivative, let's use a more concrete example. Say we need to differentiate this function, the derivative of arcsine. This happens when we need to come up with a Taylor series expansion for arcsine. I'll explain more in the future. One way to differentiate is through the definition. But this requires an understanding of this inverse square root operation, which we don't have right now. When it's hard to do so, we can view this complex relationship as made up of other simpler ones. Now the question is, what kind of basic relationships are here and how they are combined? Let's use this power format instead. Say this original function gives us the final output, y. So y and x is related through the original function f. The derivative f prime is how fast y changes with x, which is the limiting ratio of the two changes. How to get this? Here's the trick. We can think of the original function f in two layers. First, we do 1x squared on it. Then take negative 1/2 square root. So we think of an intermediate output u. Now, y can be thought of relating to x through two layers. First layer takes the input x and turns it into intermediate result u. Then takes u and turn it into the final output y. For its derivative, because it's hard to know how fast y changes with x directly, we also think in layers too. We first compare how fast u changes with x, then how fast y changes with u. So the speed of y in terms of x can be understood as how fast u changes with x times how fast y changes with u. The limit of the product can be broken into the product of two limits. We can recognize this one. This is how fast u changes with x. Now what about this term? It's tempting to say that this is how fast y changes with u when delta u approaches 0. But this is x. However, there is a connection between u and x. When x changes a little, so does u. This is the property of a continuous function. We'll explain that in the future Udemy course. Hence, this limit is equivalent to the limit when delta u goes to 0. Therefore, this, indeed, is the speed of how fast y changes with u. Now if we give the first operation a name, function h, so how fast u changes with x can be understood in terms of how they're related through function h. So this is the derivative h prime. We call the second operation function g. So how fast y changes with u can be understood in terms of how they're related through function g. So this is the derivative g prime. Now to get what this f prime is, all we need is to find out the derivatives of these two simpler ones. It's fairly easy to get h prime first. It's 0 minus 2x. For negative power of 1/2, the same differentiation rule applies. So this derivative of f is this product. But there's one problem. Only x is the known here. We want this derivative to be in terms of x. So we just need to replace this intermediate output u in terms of x by using function h. So if a complex operation can be thought of as performing an operation h first, then use that intermediate result as input to another operation g, then its derivative is the product of the two simpler ones, with the intermediate output expressed in terms of x. This is the chain rule for differentiation. So now we have these additional differentiation tools for constructed relationships. Next, we will see the corresponding combo rules for integration. In this video, we will finish our integration arsenal with two important rules: integration by parts and substitution rules. Not surprisingly, these integration rules correspond to differentiation rules. So we're going to approach the integration rules as comparison to the differentiation rule. If we combine two functions by adding or subtracting them, then the derivative is the derivatives of the two individual functions added or subtracted. This is easy to see. We also have corresponding rule when we integrate. If we integrate the sum or the difference of two functions, then it's equal to adding or subtracting their integration separately. Then the product rule for differentiation. If you multiply two functions, then the derivative is a mixed product sum. Now, what if you integrate a function made up of a product of two functions? If you can easily identify one function as the derivative of another function, say, this guy is the derivative of another function, then it equals to the product of the two functions minus the integral of this mixed product. You still have one integration to finish, but hopefully this one is easier. This is called integration by parts. Before we talk about why it's true, let's see how this can be helpful. Say we want to integrate this product. We can easily recognize that cosine x is the derivative of sine. So cosine x is h prime, x is gx. According to this rule, it is the product of the two subtracted the integral of x prime times sine x. This integral is easy because x prime is just 1. Hence it becomes integral of sine, which is just negative cosine x. But you have to be careful which one is g, which one is x. So we can also view x as the derivative of 1/2 x squared. But now, following this rule, we end up with an integral not easier than the original one. Okay, so we kind of see how to use it. Now let's see why it's true. It comes from using the product rule in the reverse direction. If we integrate this guy, based on the addition rule, it equals to the integration of these two. This should give us back fx, which is the product of the two. Move this guy to the left. This is the rule of integration by parts. For a composite function, we have the chain rule for differentiation. To integrate it, the substitution method is used. It's a bit difficult to comprehend on the surface, but basically, this integration runs the chain rule in reverse direction. This means we use chain rule to get the derivative of a composite function. Then, according to fundamental theorem of calculus, if we integrate its derivative, we should get back the composite function. Seems like whether to differentiate or integrate a compound function, once the two layers of operations are identified, it's easy to get from one side to the other. However, to identify them, it's relatively easier in differentiation, because the two layers are given explicitly. For example, what is the derivative of this function? It's easy to spot 1 minus x squared should be the inner layer, giving us the intermediate result u. And this is the outer layer. It's relatively easy to get a derivative for these two simpler operations. Then, according to the chain rule, its derivative is the product of the derivatives of each layer. Then replace u with the inner layer function. This is the final result. Now, to integrate this derivative, according to the inverse chain rule, if we can identify the two layers of operations, we should get the integral easily. But it's not easy to get the relationship, because each layer is not that straightforward. Two layers are given implicitly. It relies on your familiarity with the function derivative pair. So, how to figure out the two layers? First, the derivative should be a product of two functions, each containing x. Then you need to identify the inner layer through recognizing this pair. You should ask, which one could be the derivative of the other? Obviously, this x could be the derivative of the x squared one. So, 1 minus x squared is the inner layer, giving us the intermediate result u. Its derivative is minus 2x. Once the inner layer is known, the hint of an outer layer can be known. Now the integrand can be viewed as u to the power of negative 3 over 2 times negative 1/2 u prime. This is because we have only x here, but the derivative has minus 2, so we need to offset it. We don't get the outer layer yet, because this is just the derivative of the outer layer. So whose derivative will look like this? This guy, g of u, as u to the power of negative 1/2. This way, we know the integral should be function g of u. Then replace u with the inner layer function. This is the final result. So it takes more steps to integrate a composite function as compared to differentiating it, because the two layers are given implicitly. Let's do another example. Say we want to integrate this guy. We want to find the formula after integration. Because we know the result of chain rule could be viewed as a product of two functions, So rewrite the integrand in the product format. First, identify the inner layer. This is through thinking about which one could possibly be the derivative of the other. It's obvious that x squared plus 1 should be the inner layer, creating u. Its derivative is 2x. Now the integrand can be viewed as u to the power of negative 1/3 times u prime. Then figure out the outer layer based on its derivative. Which function, once differentiated, would give us u to the power of negative 1/3? It should have u to the power of 2/3, because, according to this differentiation table, after differentiation, u to the negative power 1/3 would appear. But a constant 2/3 would also show up. Hence, we also need an offsetting constant, 3/2 in front. So the outer layer should be 3/2 times u to the power of 2/3. Rewrite the integrand. Now we know the integral should be the outer layer function. Then replace u with the inner layer function. This is the answer for this integral. Now we have these tools in hand, let's finish the integration table. The first is to integrate arcsine. First, see the integrand as arcsine times 1. Then think of this 1 as the derivative of x. And then by using integration by part, it equals to the product of the two originals subtracted the integral of the two functions switching places. So now we need to integrate arcsine prime times x. And we know the derivative of arcsine is this guy, inverse square root term. It can be rewritten in the power format. When doing complicated integrations, the first trick is the fundamental theorem of calculus. If we can recognize the integrand as someone's derivative, then that someone is the integral. But for complex functions, it's hard to do so immediately. However, we can do it through layers. And then by using inverse chain rule, we can get the integral. First, identify inner layer operation. Think of the 1 minus x squared as function h, giving us the intermediate result u. And its derivative is negative 2x, which is u prime. Hence, the integrand can be viewed as u to the negative power of a half times negative 1/2 u prime. Now, whose derivative will look like this? This guy, g of u, as negative u to the power of 1/2. Now, the integrand can be viewed as the product of these two derivatives. This way, according to the inverse chain rule, the integral should be function g of u. The last step is to replace everything u in terms of x. Plug it into here. This is the integral for arcsine. Next, let's integrate log x. Here, we use symbol ln to be clear this is the natural growth rate. The trick is the same. Think of the integrand as a product of itself times 1. Now view this one as x prime. Using integration by parts, we have ln x times x minus another integral with the two functions switching places. Ln becomes ln prime, x prime becomes x. First terms stay the same. Ln prime is 1 over x. So the second integral is really easy. Integrate constant 1. Whose derivative is 1? That's x. So the integral of ln x is ln x times x minus x. Okay, so now we have finished the integration table and differentiation table for the 6 fundamental functions. There are many ways you can combine those fundamental ones to form new functions, and then try to differentiate and integrate. Those are the ways to practice your calculus skills. But playing with math symbols is not my top interest. My interest is in seeing how those fundamental functions can be used to analyze and model the world around us. But in order to be able to use those fundamental functions, we need to turn them into math operations. That will be the focus of the next calculus course.